This is Chapter 4, Part 1. We had an in-class lecture, but I wanted to make this available for you as a recording so you can watch it online to help with your understanding. This runs in parallel and in concert with Appendix B. If you haven't watched Appendix B, Part 1, I'd really watch that right after this or right before this. It's your choice, but it'll really, those two together kind of bring you up to speed with digital logic design, circuit design, the instruction set architecture for the CPU of the computer based on a MIPS architecture. So that's what this is going to go over. It's going to go over some of the basics. Up until this point in class, going through Chapter 3 and Chapter 2 and Chapter 1, it's been really focused on assembler language and on instructions. It's gotten highly specific in that, but kind of generalized and been vague about the logic and the data path and how that data path works. All right, I just talked about what we're going to talk about. So let's start with some small instructions. And the way the book sets this out in Chapter 4 is we basically work kind of trying to build a bridge between the instructions and what the digital logic looks like. So one of the ways we can do that is we can pick some simple instructions in the set that are easy enough to understand their management, and that there's very simple things being accomplished, like a load word, store word, add, sub, and, or, set less than, branch, equal, and jump. Okay, and we have looked at what the machine code is, but we had no clue what that means. Well, we're going to focus in here, see how the Dr. Glock in the book has broken these up by their different values, their function, their opcode, their read and write registers, and if there's a shift or not. And for example, the load word, store word, and jump, right, they all have address values here, or an offset, because they're dealing more with memory, right, whereas these are dealing more add, sub, and, or SLT are all dealing with ALU or arithmetic. So another way to look at them is like this, right? This kind of explains out what I said, what they each, putting them in categories, right? They all have to fetch, so they have to first fetch the instruction, right? And then they almost all increment the PC at a minimum by 4, right? Because the next instruction except for jump, right? Because the jump is going to go exclusively to the address listed in the instruction. And then if it uses the read registers, if they use write registers, and if they do arithmetic, so you can see all these right here basically add, sub, and, or do the same thing. Set less than, right, that's going to require a compare, so it's kind of separate arithmetic, and we'll cover that in Appendix B. Load word and store word are going to do address calculations, right, because there's some sort of address offset they have to calculate, and they're going to work with memory to do that. Branch equal, right, is a little different than load word, store word. It will use a compare. It will do address calculation, but then we'll branch to a target versus memory, as load word, store word do. And then jump, I already said, is pretty exclusive, right, on its own. Okay, so if we kind of put all that together, we can kind of get this. Well, what is this, right? Well, this is a very simplistic and basic initial model, because this section in Chapter 4 and Appendix B use kind of a bootstrapping method to put it together piece by piece in hopes that as the student you'll understand where all these data paths come from. Well, this is what this is, right? Appendix B and Chapter 4 here explain what each of these parts are, right? We have multiplexers, we have arithmetic logic units, and or gates, a NOT gate, which is just an inversion of whatever you put in. So 1 comes out 0, 0 comes out 1. And FYI, oh, by the way, we can simplify this, and usually just a little dot circle, open circle is used. So if you want to turn this AND gate into a NAND gate or a NOT AND, you just put a little circle in front of it. If you want to turn this OR gate into a NOR gate, you just NOT OR, you just put the little circle out here. And if you want to invert any of their inputs, right, these are inputs, inputs, outputs, you just put the little circle there, okay? We also deal with registers, right? Formally in the drawings will show register file. Okay, we deal with data memory and instruction memory. Okay, so we're going to separate them out here. And then we deal with some really cool simple operations that don't necessarily need to go through arithmetic logic unit, like shift left 2 and sign extend 32. Well, you might ask, how do you not need the arithmetic logic unit for that? Well, this logic unit will show in Appendix B, and later, yeah, it's all in Appendix B, how that works. So I'll show you right now how these work. Well, if you're just extending a sign, right, all that you're doing, right, is replicating the sign bit. So you just take whatever is in the sign bit position and then replicate it. So you can literally put 16 wires here and then connect the last, if we call this the last one or the first, depending on your bit order, right, and just extend it out to these other 16. Now we have 32 bits that was extended from 16. Likewise, 2-bit shift, right, if we're doing maybe some multiplication, some sort of shifting, right, same thing we can do with wires here, where these have 0, they're deasserted, right, and then these are dropped. Okay, so that's why we don't need arithmetic logic unit for things like this, shift left 2 and sign extension. Okay, and that's what all of these symbols are. Appendix B does a much better job explaining them. Alright, and this is now where all that folds together, right, where we have some simple add. We start with a PC, let me see if it spells it out here, it doesn't. We start with a PC memory, right, so 32 bits here for PC, and then instruction memory, and then registers, and then the ALU, the arithmetic operations that are performed, and then data memory, and then we just kind of follow this path. Now, different paths equate to different instructions, right? But this is not holistic or true, okay? This is just a sample model, so don't get stuck on this. First of all, right, you can join wires together, but you're not going to get the intended result, right? So we need to add path control, is what this is saying, right? So we add multiplexers or muxes, right? That was that symbol on the last page. You saw a mux is multiplexer. So it takes multiple signals in and a single signal comes out, right? So when we replace these wires, right, with control, it gets a little more complicated. You can see this and this right here kind of are easy mux, right? But this and all control of this logic need to be represented. So we get this, right? See how it pans out to each of the different controls now in each of these different areas, okay? And for all the muxes, right? So now we introduce these muxes, but we also need to introduce a control for these muxes that we added, okay? So let's talk about some basics in logic design. Low voltage, we're going to consider 0 for the purpose of this class. High voltage, we're going to consider 1. And notice we're not doing multiple voltage reading here, or multi-voltage. We're not going to have voltages in between. It's 0 or 1. Not realistic, but what we're going to do for the class. We're going to presume 1 wire per bit, and that if you need multiple bits, then you need multiple wires. We're going to divide logic for simplification into 2 types, combinational and state or sequential. Combinational is where operations are being performed on existing data. State is where there's stored information, so it's reading or writing information. Here's a pseudo Boolean arithmetic representation of the gates we looked at earlier. So you see the AND gate, right? A and B, and then the output and what the formulas look like. This is a PowerPoint issue. This should be a little block. That's not a -y, okay? And then this is what an adder does, what an AND gate does, what a multiplexer does, so it chooses paths, right? And arithmetic logic, okay? So it performs some function because you can do multiple things within the ALU. So that's combinational elements. Here's sequential elements, all right? So stored data. Appendix B, we talk a lot about a flip-flop or latch, right? And basically your data wire your clock cycle, and your output. Okay, so here you can see that it's only triggered, and in this class we're going to use edge triggering, so things are only going to trigger on an up or down. In this demonstration it's only being triggered on up. In real life this would be a smooth curve, but we're going to pretend it's instantaneously 0 and then it's instantaneously 1 at some point later in time. Alright, so these are flip-flops or latches, and what they do is basically we're looking at sequential elements that when we want to store a value, we base it on the clock cycle. Now, there's a better version, right, that's triggered when the write is asserted. So when the write is asserted, +1, the clock is asserted, there's a 1, then it will write whatever's in the data. There's a little delay in this circuit here for it to be written into the circuit. Now it's changed states. Perhaps it was 1 before, now 0 before, now it's a 1, or it was 1 and now it's 0. Okay. Appendix B talks a lot about clocking methodologies, but there's a lot of different ways to do this, synchronous or asynchronous, between clock edges, what happens. We're going to presume synchronous in this class, and that, again, we're focused on clock edges, rising or falling, not in between, okay? And that when we put both state, sequential logic together with combinational logic, now we're going to be dependent on clock cycles. Not because the combinational logic, perhaps there's some long data paths in there, but mostly because the state elements are dependent on a clock cycle. When you put all this logic together, your longest data path theoretically can be used to determine your reasonable clock period. Okay. I kind of talked about all this already, that this is what we're going to do, and I mentioned this, we're going to do it in an incremental style, so one at a time, putting everything together. So we're going to focus on just fetching an instruction first, right? So if we have a 32-bit register for the PC and we fetch an instruction, right, we're going to take what was at the PC, we're going to read that address, right? We're going to increment the PC counter, and out is going to come our next instruction because we decoded it. So there's some fetching and decoding going on here. I guess not decoding, but fetching. So we fetch to the instruction. Okay. For an R format instructions, right? Here is the logic that we're going to need, right? We're going to use read register, a register file, right? And the ALU, and we're going to use ALU result. Notice how we're not using 0 here. We have to select the operation. For load store instructions, right, we're going to use data memory logic, and we may use the sign extend logic. Okay, and so I already talked about deconflicting sign extend offset versus ALU. For branch instructions, right, we're going to use ALU to subtract, because realistically, right, when we check if they're equal to 0, we talk about this in Appendix B, we can subtract the two and see if they're 0, to find out if they're equal. If they're not equal to 0, those two data values, registers, right, when they're subtracted, were not equal, if subtracting them doesn't equal 0. Okay, here's some additional things for branch instruction that need to be accomplished. Here's the logic, right, that performs all of this. So the previous ones could all fit on one slide. This one takes 2 slides because of the operations that need to be done and showing the digital logic data path circuit. So here's the data path circuit, right, the instruction for reading, for shifting, for branching, so the resultant branch target and branch control logic, and maybe there's a sign extension that has to occur there. So this is just the basic fundamental parts we need. I already talked about those. So first cut data path presumes we do one instruction in one clock cycle. That means no pipelining. Part 2, we're going to go over pipelining and kind of pull back the curtains and show what's really there behind all of this, and kind of bring this picture to completion. But in the basics, we're going to have a separate instruction and data memories, and each data path in this big picture will only do one function at any instance of time, one time, right? Okay, so putting together R-type, load store data path, we can kind of combine them, right? So we're taking the parts of R, right, those parts, load store, and we're putting them together, right? And we can now create multiple paths, right, depending on what is being accomplished. But recognize now there's paths that aren't necessarily used for all these instructions, okay? So what about an add, right? Well, an add, for example, can also be done here, right? Not in this type, right? So it's going to read T1, T2, right? And it's going to output those data values, right, into the ALU. The ALU correct operation has to be selected, right? ALU op add, ALU source 0, right? And the memory write, memory read. So 6, you notice how there's 6 values here. I want you to notice that for later, okay? It's going to help select the paths in all of this, coming through these different controls. Mem write, mem read, mem to read. Oh, here's mem read, sorry. Mem read, mem to register, ALU op, ALU source, and registry write. Now notice the write doesn't actually occur until the end. It gets all the way written back. Okay. Putting it all together, right, with the PC incrementing and this R load store data path, we put this. We've now constructed. We know this is going to work because it's a fictitious example because we've already seen the end of it, or you're going to at the end of chapter 4. But this is kind of putting it together so you can kind of see where the different instructions now work. Well, every instruction, except for branches, right, a control path change, is going to increment by 4. So we add this additional data path up here, right? That every time it adds it, increments it by 4. If some sort of branch or something was happening, or a jump, right, then it might further change the next address, and then it writes it into the PC. But for R, load, store words, I already showed those paths, right? But there's one other path we're missing here, right? And I'm going to show it here, a jump, right? If we do a jump, we need additional logic, right? Because we don't have to do, I mean, you can do it, but the adding it's not going to hurt. But essentially, we just need to bring in the jump address, right? So we can just bring it in from instruction memory, right, and jump, write it out into that address, okay? Where'd all this stuff coming from in between? Well, those, remember I said, hey, I want you to notice these 6 values for controls right here that go into each of these. Let's look at that now, right? So here's 4 values for ALU control lines, so that's just specifically here, okay? But so here's our ALU op, and here's our ALU control. All right, so here's the arithmetic operation. Here's the what type of output is needed, okay? And here's the instruction opcode, which is these 6 values I told you to focus on there, right? So 1, 2, 3, 4, 5, 6. ALU op for the output needed, the ALU control for the arithmetic, right? And this kind of tells where all this stuff is going and what it means. It decodes it for you. Here's some example of how these are set for different instructions, right? So here's your R type add, okay? So the add instruction, right? Here's what the function field is. We haven't talked about that yet. And then here's what the ALU control is, add, and the ALU is going to be 0010. And in this case, right, it's being written to a register, so it's 1. That's the destination code. So we can build a digital logic path, that's the basic idea here, out of combinational logic, right? And we could also theoretically do it with a ROM, but combinational logic is easier because of the number of inputs, right? So how do we determine the ALU opcodes? Well, we construct binary arithmetic, and we go over that in Appendix B. But here are some samples here just to kind of get you primed for Appendix B, okay? Here's again a sample. Appendix B goes more specifically on what the different opcodes do into each of their gates, okay? Because this is what we're really looking at, is this control path, right? So let's go into this control path, right? Here's the control path. And you can see it adds some additional ones we didn't have there earlier, right? Like register destination. I don't think we had register destination earlier. Hold on. Yeah, we didn't have register destination, and we didn't have, did we have register write? Register write. Well, you can pause and compare the two, but 1, 2, 3, 4, 5, 6, 7, 8. So 2 of these are our additional opcode here for I believe it's ALU op, I think here. So we get the 6 values, right? That build up to the opcode. Okay. So not sure if that's correct. I'll have to double check that, but here's my point. This is a MUX. It's a control unit. As you're putting the different inputs in, right, the MUX built on these gates is going to determine, right here, you can see the ALU op. Okay. This gives the example for cycle control, what different assertions and deassertions of each of these will do. All right. So for example, if register write is deasserted, then do nothing for register write. If it's asserted, the register on the right register input is written with the value on the right data input. So like we saw earlier in the registry memory, right, then you're going to assert the write wire, and whatever's on the data wire on the next clock cell is going to be written to that the register memory that those wires are connected to. You can pause and look through each of these or in the book. Okay, so here's the data path. Now we're building and building. Again, this doesn't have the jump logic in it yet because that's near the end, but I touched on it already. Here you can see the cycle control, right? It's kind of like the controls on your washing machine. What do you want it to do, right? Wash, rinse, what do you want it to do, right? And this will help control each of these branches through the different muxes that we've added and the ALU control, right? The ALU op that we added on there. Okay, so for example, right, here's R type instructions, what they're going to use, right? So some sort of arithmetic. We're going to go through each of these different. We're definitely going to use control. We're definitely going to use ALU. Definitely going to be using registers, right? See how memory is grayed out. We're still going to have to fetch the instruction, right? And ALU control, obviously, to determine what the ALU is going to do, right? That's the ALU op right there, okay? Load instruction, right? Still control is necessary. ALU is also still necessary, but now see, although it doesn't completely become dark, right? We use data memory, okay, and still using certain register memory, okay. But on branch equal, right? You can see we're only using reads here. We're not writing it. We're not using data memory, right? But we are definitely using all of our logic. See how it wasn't used here for load instruction? Here it will be used, the logic to correctly increment the PC counter, because on branch equal it may not just be 4 anymore. Okay, so this logic this time, right, is also queued up, right? And this is how, right, if it comes out as 0, right, then they were equal to each other, then the branch is going to occur. So that's going to select 1 out of this path instead of 0, right? That gets fed back. So the new address will get fed back instead of just incrementing by 4. Okay. Already talked about jump to implement the additional jump logic, right? You see it right. You can see where it goes. It's not here, right? We have register, destination, branch, memory. I kind of showed this earlier. Now we put the jump logic in there, okay, for where we need to add this additional mux. because this was for branch or PC. Now after that we also need to decide, is it a jump? Okay, so jump gets its own data path, kind of in a way, manner of speaking. So I already mentioned this. Theoretically, your longest delay in that path is going to determine your clock period. Okay. There's different methodologies on this, but essentially we want to make the common case fast and not violate the design principle. Okay. We can improve this later by pipelining. That's it for part 1. Part 2 goes into pipelining and all the other details that are needed to, in concert with Appendix B.